Okay, so probably two videos for this topic. First, going to talk about what is a maximum likelihood estimator, and do some examples, and follow that up with some useful properties of them and some more examples. And that will do it for chapter 9 from the book Mathematical Statistics by Wackerly and others. Okay, so here's a definition. So we have a sample of observations, little yi's, that are from an IID sample, capital YI's, so just the usual setup, and with the parameter theta, this could be a vector. And so then the maximum likelihood estimator, which we'll abbreviate with MLE, we'll write like this with the hat to mean estimator and put the MLE down here in capitals as a subscript. And it is the value of theta as a function of capital Y that would maximize the likelihood. Okay, so we'll work with the lowercase y's. That's what we have. And we're trying to maximize this likelihood function with the little yi's as constant and considering the theta to be not constant. So something that we can pick the theta that makes this number the biggest. Okay, so let's just jump in with an example. So this will just show you exactly what it is. So suppose we have, let's say we have y. So we have y I observation, y bar, little y bar from which is modeled to be Bernoulli P. So in other words, n, the usual thing, say just a general n samples. And so then first thing you do is you write the likelihood function. So L little y P. Let's just write it out again. This is 1 to n. Let's just put it in now. And here we have P I 1 minus P to the 1 minus yi. Okay, so we just want to maximize. We're thinking of the little yi's are observations, even if they're not set yet. And we want to maximize this function with respect to P. So often we will want to take a derivative. Okay, so let's go for that here, I think. So let's just take the derivative here. So I have d dp L y P. So look, this is kind of a mess. We don't want to use the product rule with all of this. So let's first apply this product, and then we'll take the derivative of that. So ddp, I have p to the sum little y. I remember the y's are constants in this, what we're doing here. And 1 minus p to the n minus sum yi. The variable is p. Okay, good. We still have one product. There's a way to avoid even that, but let's go ahead with the product rule here and differentiate. So we get this is equal to, I think we can fit it here, derivative of the first piece, which would be sum yi p to the sum yi minus 1 times 1 minus p n minus sum yi. No, we can't fit it on 1, plus the derivative of the second piece, right, with respect to p. You see, you're going to get a minus sign from the chain rule with the second term, so I'll just write it now. So minus p to the sum yi, and now I need to differentiate this. So I have n minus sum yi, 1 minus p to the n minus sum yi minus 1. Okay, this looks pretty bad, but it's not too bad. I can factor a lot out. I want to set this equal to 0, right, to find a extreme value for the likelihood function. So what I can do is let's factor out this piece here and this piece here. We'll take these outside, and we're going to assume P is not 0 or 1, and so that this will kind of go away. So P to the sum yi minus 1 times 1 minus P to the n minus sum yi minus 1 will come outside. And then what's left over is the rest, right? The rest. So I have in here, I have sum yi, and I have 1 minus P. And over here I have minus P times n minus sum yi. This is pretty ugly, but it's not too bad. Now this is not equal to 0, right? So so we need to set this equal to 0. So ddp ly bar given P equals 0 if this equals 0. So, or if these two terms equal each other. So if, let's see, can we simplify this? It appears we can. If sum yi minus P sum yi, let's do it like this, is equal to NP, I'm adding it, minus P sum yi. So you can see these will cancel. This cancels with this. So that's true only if P equals 1 over n sum yi. Okay, so this is the function in terms of the observations for P. The one that will maximize the likelihood is if P is equal to the average of the observations. So just to write the MLE estimate, you go back to the random variables. So, and let's agree we'll always use this notation. The MLE estimator for P is just equal to 1 over n sum yi, or we've been writing it like this. Okay, remember the yi's are Bernoulli, so we're going to get some number between 0 and 1 for this. Okay, so y bar is the MLE. You can't always do the differentiation for certain problems. So here's another example where you don't really want to use differentiation here. It won't work. You have maximums sometimes at the edge of the domain too, right? Where it might not be differentiable or the derivative might not be a max, but you are at an edge. The derivative might not be 0, but you're at an edge. So for example, 2, we have one of these. So suppose we have y1, yn, and let's have it be IID uniform 0 to theta. Okay, well then we've seen already that the likelihood function equal to the product 1 over theta, but I also have to control for the observations being between 0 and theta. So I think the way we do this is, we'll use an indicator function, and let's just put 0 to theta here, yi, which we can now summarize like theta to the minus n. And for this, we're going to write it like this: 1 minus infinity, it's got to be between minus infinity and theta, right? This is where yn has to be the max, and 1, the min has to be bigger than 0, so 0 to infinity. Notice they can't go outside the range like this because y sub n in parentheses is the max. So So if the max is less than theta, the min can't be greater than theta, but this is a good way to write it. It shows the right factorization, I think. All right, so you don't really want to take the derivative here. The idea is you want to pick theta based on your samples that would maximize this quantity. Well, clearly, you don't want it to be zero. So you don't want zero is not going to be the max. So let's maybe write this. So Ly is clearly equals 0 will not give the max, because we can pick values that are bigger than that right away, right? Like anything that's valid. So just think about it for a minute. These are always 1 or 0. So these should both be 1, right? These should both be 1. So we want the value of theta that would make this the biggest. So overall, so the question is overall valid theta, which means theta must be bigger than y sub n or equal to, or else it's not valid. You couldn't have a theta less than yn. We want the theta that maximizes theta to the minus n, or 1 over theta to the n. Right? Yes, 1 over theta to the n. We want that to be maximized. Okay, well, so wait, somebody hold on a second. So it has to be bigger than yn, right? The biggest one in the sample. Otherwise, you couldn't have gotten this max one. But we don't want it any bigger than this, because as you can see, it could be bigger. But if I'm trying to find the theta that maximizes the likelihood, then I want to pick it right at yn. Why? Because theta to the minus n is a decreasing function. So it only makes the overall likelihood smaller if I pick a number bigger than the max of the sample. So I want to pick it right at the max of the sample, right? So overall valid theta bigger than or equal to the, we want to maximize bigger than or equal to the max. We want to maximize theta that maximizes theta to the minus n, since theta to the minus n is decreasing. We pick smallest value possible for theta. So theta hat MLE should be equal to y. Okay. All right. So that was a case where taking the derivative wouldn't have worked. Okay. It would not have done anything. All right. Wonder if we could. Yeah, I think that's fine. Okay. Here's another example. So suppose we have y1, yn, IID normal mu sigma squared, both unknown. And so we're going to need partial derivatives to find an extreme value in terms of mu and sigma squared, right? We could just proceed as last time, but keep in mind the likelihood, right? L y given, say, mu sigma squared is it's a function from R2 to R, right? So we're going to need partial derivatives. And this will be, yeah, so the range is just a number, right? And if I take the log of the range, since the log is increasing, so then I could just work with the log and maximize the log of this, and that will give me the same mu and sigma squared that maximize the likelihood. So we'll say this is maximized at same mu sigma squared as its log, which we'll write like this, little l y, and just equal to the natural log of, say, this. Okay, so I'll take this function here, and we'll take the log of it, maximize the log over mu and sigma squared. That same pair that maximizes the log will maximize the likelihood as well. All right, so let's write this out. So we have L y is just equal to, so remember we've done this now once or twice, so I think we can just write this down. It's 2 pi sigma squared to the minus n over 2 times exp minus 1 over 2 sigma squared summation yi minus mu squared. Okay, so that's that. So let's take the log of that. I have L of little y, and this is equal to taking the log of this, log of a product's sum of the logs. So we have minus n over 2 log of this product. I could write that as a sum as well. Let's write log, yeah, what the hell? Let's write log sigma squared plus log 2 pi. Okay, so that's the first term, plus the log of the exponent, their inverse function. So plus minus 1 over 2 sigma squared sum yi minus mu squared. Okay, so this is our this is the function we're going to maximize over mu and sigma squared. So we want the couple partial derivatives. So we have dl y d mu. This whole first piece goes to 0. So differentiating with respect to mu here, we get this is equal to the minus will come out, so I get, and the 2 will come down, so I get 1 over sigma squared sum yi minus mu. Setting this equal to 0 leads to the fact that mu equals the average, right? The sample, right? So this leads to n equals n mu. And so mu MLE equals the sample mean, right? Equals y bar. Okay, maybe a little premature because we want to think of both points together too. So, but let's be optimistic. I already know the answer. So, dly d sigma squared. I want to take the derivative now of the log of the likelihood with respect to sigma squared. Here I have a little more work to do, but it's not too bad. So this is equal to, all right, so I'm taking the derivative just of this. This is 0, so I don't have to worry about that. This would be minus n over 2 sigma squared. And now take the derivative of this with respect to sigma squared. So this is sigma squared to the minus 1 power So I multiply by -1, I get a positive number, and I drop the power, so I get +1/2 sigma to the 4th summation yi minus mu squared. I really want to put the y bar in for mu too, right? Because these are simultaneous equations, so I want to solve for the pair in R2. So this should become y bar. I'll do this on the next line. So we set this equal to 0. And we can cancel a few things. So I have, if and only if, let's do the substitution too. So what do we get? The 2's go away, and we should get, the hell. So I add this over here, multiply, cross multiply, so I get sigma squared. Yeah, sigma squared equals 1/n. Let's put it in y bar squared, substituting our solution above, mu equals y bar. Okay, so let's write it as a vector, mu sigma squared MLE is equal to y bar, and then this expression here, which is 1/n sum yi minus y bar squared. Or could write this like this too, y bar, and here we could multiply by 1 here, n-1/n minus 1, and write it n-1/n s squared. Okay, you recall y bar and s squared were sufficient statistics. Our MLE is a function of those, and you will see this is going to be true in every case. It's one of the properties. All right, I think that's going to do it for part 1. We'll have part 2 next, following up on this very idea.